Okay, let's do some calculus. This is tangents and the derivative at a point. So previously what you've learned is we started with finding the slope of a curve at a particular point and how to measure the rate, because remember when we talk about slopes we're talking about rate at which a function changes. Well, now wait for it. We're going to find a tangent to the graph of a function. Remember when we first started talking about secant lines, and we said that a secant line is a line on the graph that touches it in two places. Okay? Now we want to move to our tangent line that says we only touch the graph in that one spot. Well, think of how you could do that. This right here says calculate the slope of the secant through a point and then a nearby point. Well, what if I got a little bit closer? And what if I got a little bit closer? Meaning I'm moving this point closer to my point of interest. If you notice what's happening, my h, my distance from the 2 points, is getting smaller and smaller and smaller, and it's going to 0, which, remember, is the definition of a limit. So see, there is something you can use this stuff for. So now I can see that by my definition of my limit, because I have an understanding of what a limit is, as I'm letting h, the distance between those 2 points, get closer and closer, goes to 0, then what I'm doing is I'm finding the slope of this tangent line at that particular point, which is nice to know, because at this particular point I may want to know how something's changing. You know, what's the rate that it's increasing? Alright, so let's actually go through an actual example to see how to do this. So what if I wanted to find the slope of a curve at any point for this function? Well, what I'm going to do is I'm going to start with my definition, where my definition is the limit as h goes to 0 of my f of x. Well, I want any x, and so we're calling that a. So a plus h minus a all over h. And now we know from working with the limits that we take and we plug a plus h into our variable, and then we plug in a. So I get the limit as h goes to 0 of 1 over a plus h minus 1 over a all over h. Alright, I know it looks kind of scary with all those fractions, but what I'm going to do is actually make one fraction. So we remember to do that we've got to get a least common denominator, and I can do that by just multiplying those. So in other words, my denominator is going to be a times a plus h, and so then most students will say cross multiply, or I'll say what's missing on the first one, and so you can see that's an a. And then on the next piece, my 1 over a, or cross multiplying a plus h. One thing you have to be very, very careful of is you are subtracting all of that a plus h. Okay, don't lose that minus sign, because you're going to end up distributing it. And then of course all of this is over h. This isn't so bad, because I can now see that a minus a is going to cancel. I didn't forget to distribute my negative sign, so I'm going to get negative h. And then I'm going to pick this up and move it down to the bottom. So I'm going to have h and then the piece that I moved. So I got ha and a plus h. Alright, looks like we're home free because my h's are going to cancel, and that's what we like, because I would no longer be dividing by 0 if I plug in 0 for h, which let's do it. So that's negative 1 over a times a plus 0. which is going to give me a negative 1 over a squared. All right, now we said that this is going to give me the slope of the tangent. And you might say, well, that don't look like any slope I've ever had. Well, we're saying at any point, so give me a point. What if you want to know what the slope is at x equals negative 1? Well, guess what? You take this and you plug in where you see an a, you plug in negative 1, and you get the slope. So it's kind of nice because now I'm saying that we can find the slope. We don't have to have a particular point. When I went through all of these steps, I actually came up with a function that allows me to plug in for any point. So the big deal here is we started with this difference quotient, and then we added this limit piece, which this is the huge part, because remember visually this was moving my secant line, that second point, closer and closer and closer to the first point. In other words, the distance of h was going to 0. So when adding this limit piece, this becomes the definition of the derivative. So our derivative function, f at a particular point, you will see this written, this is one way, we'll talk about different ways to write derivatives, but with this prime, so we call it f prime of x naught, which says that our difference quotient was just the average rate of change. We wanted to know on average what's happening between 1 and 2 o'clock. Now the big deal is I want to know what's happening at exactly 1 o'clock. And that's my instantaneous rate of change, which is my derivative. And so what's cool about this is so many students, when they get into calculus, they're like, oh, calculus is so hard. This is a very difficult class because we have to find derivatives. Well, all a derivative is you're just finding the slope. Because if you notice, this was my definition where I had an m out front. And so if I want to know for any value of x, what I'm actually doing is I'm finding another function, like my negative 1 over a squared, that I can plug in for any value. And this is nice because, okay, I want to know what's happening at 1 o'clock exactly, but my boss wants to know what's happening at 3 o'clock. Well, if I have this function, then all I have to do is plug 3 in for him. You're going to hear many different interpretations for this limit of the difference quotient. Again, the big one here is it's the derivative. It's also the slope of the graph at a particular point, the slope of the tangent line. And when we get into applications, because remember the slope is a rate of change, the change in y over the change in x. I mean, we still go back to what you know from your algebra days, that what we're doing is we're finding the rate of change, the slope, which is the derivative at any point now. Is we're saying, I don't want to know what's happening at 1 o'clock. I just want a function that I can plug in any value. All right, I've always thought this was a very interesting example because students come in here and they're like, it can't be this easy, because I have heard finding derivatives was very, very difficult. It can't, you're just telling me when I'm finding a derivative, I'm finding a slope? That's what you're telling me? Okay, let's see if I can convince you. So let's say that I have this function. Looks familiar, right? Y equals mx plus b. That's a line. And I want to show the derivative at any point is the slope of the line. So if I do this correctly, I should get m, right? Because that's my slope. So if I start with what I've told you, the limit as h goes to 0, I'm going to go ahead and start with my function. So my m, where I see an x, I plug in my x naught plus h. And then I still have the plus b side. And then minus, where I see an x, I plug in x naught, and then plus b. Now I told you earlier that negatives scare me to death because I'm always afraid I'm going to miss one somewhere. So what I typically do, this part's probably not as major, but I kind of wrote these together so that way I remind myself I better not forget to distribute that negative sign later. All right, and then all over h. So the first thing I'm going to do is distribute this m. Uh-oh, almost missed my h there. And so I get my limit as h goes to 0 of m x naught plus mh plus b. And what the heck, let's go ahead and distribute this negative sign. So that'll be, make that look more like a b, minus mx naught plus b all over h. So as you can see, that cancels, and then you say, oh, but wait, Cindy, you just told me, it's where I wanted to make sure you catch this, you better make that a negative sign. Okay? If you don't group these off, mistakes like this can happen. So you want to be sure that when you're distributing a negative, you either do it right away, and I see students will do that. They'll just write minus mx sub naught minus b, or you make sure you distribute it, because now I can see the b and the minus b's cancel, and I'm left with my limit of mh over h, because everything else canceled. So nicely, the h's cancel, so I have my limit as h goes to 0 of m. Well, remember, m's just a constant, so in other words, there's nothing here, there's no h, so this is just going to equal m, which, ta-da, hopefully you're impressed that that's all you're doing. You're finding the slope when you're finding derivatives. And if you can keep that kind of in your mind, I think it helps not getting so crazy. Now, yes, of course, the problems are going to get more difficult, plugging things in, but visually, I think that helps you get through this course, because it says, oh, I want to know the rate of change at a particular time, which is finding the slope of the tangent at that particular time. An application of this. 8 seconds after liftoff, the height of a rocket is 3t squared. How fast is the rocket climbing 10 seconds after liftoff? How fast is the rocket climbing at exactly 10 seconds? I don't want to know from 0 to 10 an average. I want to know it exactly 10 seconds. Well, we know how to find exactly. That's my derivative. So I start with my derivative. I can see that I'm going to plug in 10 for my t, for my time. And then I take my function and I plug in where you see a t. Notice I plugged in my t plus h. And where you see a t, I plugged in 10. And now away I can go. So my first step, I know you remember FOIL, right? Because that would make this kitty very unhappy. So if you look at this and you're going, how did she, what happened? Remember that the meaning of this, my FOIL here, this is 10 plus h times 10 plus h. If you remember the little shortcut, you square the first term, check, 2 times these two terms, and there's a 1 there, check, and then you square the last term. All right, now I just need to do some distributing of this 3. So I just took the 3 and distributed it. And then I multiplied the negative 3 times 100, got my negative 300. I can see the 300s cancel. And now, as we've talked about before, when you're doing limits, you should be left with something that your h's are going to cancel. And so what I did is I factored the h out of the 60h plus the 3h squared, because I can clearly see that those h's are going to cancel. And no longer do I have an h in the denominator, so I'm definitely very happy. I let my h go to 0 and I get 60. Now, this is one thing I kind of have a pet peeve about. Students will say 60, and I'll say 60 what? Are we at 60 feet? Are we at 60 seconds? You really need to learn how to interpret word problems because, I mean, that's what you're going to do in the real world, right? We're not going to say 3t squared and so I got 60. So I need to know what does that 60 even mean? Remember, we're finding a rate, and that's why you kind of don't want to keep thinking slope, 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 like I started the lecture with. You want to think rate, 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 because that helps you interpret your answer and our problem solved. Woohoo! If this is a rate, this says the rocket is climbing at a rate of 60 feet per second at exactly 10 seconds. And that's the key word right there, exactly. And that gives us our definition of our derivative. Now I know you are excited to know that it is your turn. Why not give this one a try? What is the rate of change of the volume of a ball with respect to the radius when the radius is 2 inches? And of course, if you've forgotten, the volume formula for a ball is 4/3 times pi times the radius cubed. And let's see what you can find with that, and we'll talk about it next class.